is that we'll stop at around 8:30, but there are a couple of things that I would like to discuss about some special relativity paradoxes that are kind of interesting once you've learned the content of these two lectures, that is today's lecture as well as the last lecture. And so if any of you are interested in hearing that, that's not part of the course per se, but I'll be happy to discuss it after the class is over. Okay, that later today. Okay, so let's just recap where we were last time. Okay, so we talked about this idea of accelerating particles in special relativity, and what we discussed is it doesn't make sense to have a constant acceleration in some particular inertial frame, okay, S prime, because at some point then your speed would exceed the speed of light, and that can't happen for a physical particle. Okay, it would violate causality. Okay, as you might have studied in an STR course. So but what you can have is a particle with a trajectory such that it has a constant acceleration in its MCRF, which is the momentarily co-moving rest frame. Okay, and what we did last time was to figure out what is the trajectory of a particle which has a constant acceleration A in its MCRF. Okay, and what we found is that if you study this trajectory in some particular inertial frame, S prime, what you'd find is that that trajectory is a hyperbolic trajectory. Okay, it's this kind of trajectory, as opposed to a parabolic trajectory, which is what you would get if you had a constant acceleration in S prime. Okay, the constant acceleration in S prime, you can see that the slope goes on becoming flatter. Okay, as you go outwards, and what that means is basically with a parabolic trajectory, the speed goes on increasing. Right, you cover a large x in a small time, but for the constant acceleration in the MCRF, the trajectory actually asymptotes towards the line t prime is equal to x prime, which means that basically it asymptotes to something which is almost traveling at the speed of light. And similarly, it starts off with something traveling to the left with the speed minus c, and it ends up with the speed plus c, okay, if you continue to follow its motion. And the reason we were interested in all of this was we were trying to build the idea of an accelerated reference frame, okay, in special relativity. Okay, and so the first thing is we had to understand accelerated observers in special relativity, and we saw that there's some non-trivial things about acceleration in special relativity. Okay, and in particular constant acceleration. Now, one of the other things that we saw is that this is the only sort of valid trajectory. This parabolic trajectory is not a valid trajectory because your speed would exceed the speed of light. The other thing that we saw is that there is a region of space-time, okay, which is, let's say, beyond this asymptote, from which no matter where you are in that space-time, if you choose to send a light signal, that light signal would travel parallel to this asymptote, and therefore it would never reach this accelerated observer. Okay, so this is called a horizon. It's a space-time region from which no signal will ever reach the particle. Again, this is something that is unique to special relativity. The way to think of it is, I have a particle which is accelerating. I am over here in some other region of space-time, and I shoot a light beam towards this particle. Now, what this light beam has to do is it has to travel at least this initial distance to get to this particle, plus it has to catch up to any additional distance that this particle travels, and this particle is speeding up, okay, and eventually it's getting closer and closer to the speed of light. Now, the claim is that even if you shoot this light beam at the speed of light, okay, if the distance is sufficiently large, okay, then you will never catch up with that particle that you're shooting the light beam towards. Okay, so beyond a certain point, okay, of space, you can never send a light signal which will actually catch up with this accelerating observer or accelerating particle. Okay, so that's again something that's kind of unique to special relativity. Okay, and the fact that you have this limiting speed, the speed of light. Okay, now what we'll do is we want to consider accelerated reference frames. So rather than talk about a single particle which is accelerating, we'll consider a family of particles or family of trajectories which correspond to accelerating trajectories. Okay, so a naive choice of such an accelerated set of observers would be, let's take the example of what we had above. Okay, so we had something like this. So we had Ct prime is equal to c square by a sine hyperbolic a tau over c square, and x prime is c square by a cos hyperbolic of a tau over c square. We did not have this x naught earlier. Okay, So you might imagine that one way to consider a family of observers is to add a constant x naught to each x prime. Okay, so what that does is, if you note this observer over here, okay, at t prime is equal to 0, their x coordinate was c squared by a. Okay, so it just happened to be over here. So now you could consider a family of observers with the same acceleration a in their MCRFs, okay, their respective MCRFs. And each of those observers, so I've drawn the trajectories here as A, okay, this is this trajectory, B, which is this trajectory, and C, which is this trajectory. Okay, and if you look at these three different trajectories, each of them basically intersects the x-axis at a different x naught, but in some sense these hyperbolas are all parallel to each other. Okay, which means that their asymptotes are all parallel to each other. So their asymptotes are parallel to each other like this. Okay, so they're all just slightly shifted. Okay, another way to see that is if I take ct prime whole square minus x prime minus x naught whole square, this is a constant, it's c square by a, okay, up to minus I. Okay, so this is what you get. So your asymptotes are now ct prime minus x naught equals 0, and ct prime plus x prime minus x naught equals 0. Okay, so these are your asymptotes. Your asymptotes are shifted, okay, by an amount x naught in the x direction. So, so in particular, the original one, let's say, had an asymptote at c squared by a, okay, and now, sorry, the intercept was at c squared by a, and now the intercept on the x-axis is c squared by a plus some x naught. Okay, so x naught is equal to 0 was our original observer. Different x naughts now correspond to different observers. Okay, and you'd have infinite number of observers for x naught going from minus infinity to infinity. Okay, so you'd have an infinite number of these observers. And each one of them has this trajectory, and each one of them has an acceleration a in their MCRF. Okay, so each observer is A, B, C that I've drawn above is characterized by different x naught. X naught can go between minus infinity to infinity. Each observer has the same acceleration a in their MCRF. Okay. Now the other interesting thing is that if you look at some time t prime, okay, some time t prime. Now each of these observers has the same velocity, because for each of those observers, if I fix t prime, then I'm fixing tau, which is the proper time, and the speed of each observer as measured in this reference frame, that the inertial frame, is tan hyperbolic, or c times tan hyperbolic of a tau over c square, or tan hyperbolic of eta. Okay, and they all have a common tau, okay, or proper time, and therefore the speeds of all of them are the same for a given t prime. Okay, and that's also easy to see because these are parallel hyperbolas, so the tangents are parallel, okay, at a given t prime. So all of them are traveling at the same speed as measured in this inertial frame s prime. Okay. And the other thing is each pair of observers, so if I take any two observers, like let's say AB or BC or AC, they maintain the same separation delta x naught. Okay, so if one is at x naught and the other is at x naught prime, the separation between them in the frame S prime is always x naught minus x naught prime as measured at some instant of time t prime, okay, in this frame. So between themselves in the frame S prime, they maintain this fixed distance delta x naught. Okay. However, you might think that this is a good family of observers to choose for an accelerating frame of reference. Okay, but however, there is a problem with choosing the set of observers. Okay, it's a perfectly valid set of observers. So the problem with this family of observers is that, well, there's nothing wrong with them in the sense that they are a perfectly valid set of observers. However, the problem with them is that they are not simultaneously at rest with respect to each other, as seen in their individual MCRFs. Okay, so let's see why that should be the case. Okay, so they're not simultaneously at rest with respect to each other as seen in their individual MCRFs. This is a bit counterintuitive, but again, if you remember the lessons of special relativity, it's easy to see why this is true. Okay, see, the thing is, each of them, as we already discussed, okay, so if I take some instant t prime in frame S prime, each of them has the same velocity v, okay, at a common instant of time t prime. Now let me go to the rest frame of one of them. So let me go to the rest frame of A, let's say. Okay, so in A's rest frame, we want to know at a common instant of time, okay, which is this instant of time in the frame of A. Okay, this space-time point has some time t in the rest frame of A. At that instant of time, in that inertial reference frame in which A is at rest, what is the speed of B? Okay. So any guesses for what that speed would be? Would it also be 0? Would it be greater than 0? Would it be less than 0? That is, would it be going to the left or to the right?
So their constant separation by del t will give some speed.
Their constant separation in space by some delta x naught as measured in frame S prime. What about it?
So divided by del t measured in A's frame.
Divided by del t, but I'm measuring at some instant of time t in A's frame. So what do you mean by del t?
Means like from t to t plus del t in the limit del t
Okay.
going to 0.
Okay. So delta t goes to 0, but delta x naught is a finite quantity.
Yes.
So what do you mean by this quantity? This is a fixed quantity, right? This is measured in S prime, and this is measured in S, which is the rest frame of A. That's not something that you would typically do, right? Okay, let me just rephrase the question again. Okay. So here's a particle moving with a speed v. Okay. At the same instant of time as measured in the frame S prime, another particle is moving with the speed v. Okay. Now, I want to go to the rest frame of this particle A, okay, at this space-time point. Okay, so now I'm in the rest frame of particle A. Now what I need to do is I need to locate B at the instant of time t as measured in the reference frame A. What is the space-time point which B will be at the same time t? How would I find it on this in this figure?
You're asking by graphical means, or do you want equation?
Let's say graphically. Okay, let's say graphically.
Yeah, you can draw you can draw x prime and t prime, and then we can essentially find where the points will be.
Okay, so how do I draw x prime and t prime axis at this point?
Once you know v, you can then you can use the angle theta formula. I don't exactly remember what it is, but with the x-axis, there'll be an angle theta.
Right. So what you do is you first draw a light cone here. Okay.
Yeah, the light cone.
You draw a light cone. Then second thing you do is you draw the tangent to this curve. That's the speed. Okay. This gives you your t prime axis. Okay. This is the tangent to this curve is your t prime axis. And then whatever this angle is, you draw the angle on the other side as well. That's your x prime axis.
Yeah.
Okay. Now let me call this t and x. Okay, because this is in frame S, which is the rest frame of particle A. Now what I want to do is I want to locate the particle B at the same instant of time, and here I've chosen this point to be at t is equal to 0. How will I locate where particle B is, the space-time point where particle B is at t is equal to 0 as measured in the frame S?
Draw a line parallel through B. Draw a line parallel to the t equal to 0 axis through B, and where it intersects the x-axis will be the point where it will be.
Yeah, so the t is equal to 0 axis is this axis. Okay, yeah. It's just the x-axis.
Okay, and so the x equal to 0 axis.
No, this is the axis. No, you want the t is equal to 0 axis. You want the same time.
You draw it parallel to the t-axis is what I mean. You draw a line parallel to the t-axis.
Okay.
Through B, but through B.
Oh, here.
Yeah.
That's not the way you do it, right? You stick with this origin, Okay, this is still your origin. This is t is equal to 0, x is equal to 0. Okay, and this line corresponds to the line of t is equal to 0.
Yeah.
Right, because there's all the points. So basically all these points have the same time t is equal to 0. Which means this point here also has t is equal to 0, and b was at this point at t is equal to 0. Okay, does that make sense?
Yeah, but the x you've drawn is kind of like if you shifted your t-axis to b, then that would intersect over here, right?
If I shifted my t-axis to b, so that
Like
would
if
be.
you just drew a parallel line.
Sorry, it's a lot of lines. Let me just switch colors so that it's a little easier to see.
Yeah, no, you don't need to draw it, but I'm just saying that the line through B intersecting its point on the x-axis will be parallel to the t-axis.
So this axis or this axis?
So the other one.
This one.
Yeah, this is parallel to the t-axis, right?
This is parallel to the t-axis, yes.
And that will intersect at the point where B will be on the x-axis.
No, it won't, because what you've drawn here is only B's behavior at this space-time point. Okay, it's not telling you what B was doing earlier. Okay, B is not a constant velocity observer.
Okay, so this method works for constant.
If you had a constant velocity, then both methods would, I think, give you the same thing. Okay, B is not a constant velocity observer. You are basically yeah. So you can't really just shift the. You have to set one origin. Okay, over here. Okay, so in this case we set it over here, and we just have to locate where B is at t is equal to 0. Okay, and that would be this point. Okay, I think the answer would be the same if, as your method, if B was moving at a constant velocity.
Okay.
Okay, so this is a bit of a tricky thing. Okay, that you have to work out. And so now once you figure out where B is at t is equal to 0, you basically have, this is the velocity of B, the tangent measures the velocity of B at that time in the frame S prime. And what you have to do is convert it into the velocity in the frame S. Okay, so this is the space-time point at which you want the velocity of B. Okay, and that would tell you the velocity, and then you convert it to what the velocity would be in the frame S, and that tells you the speed of B in the frame S. Okay, but the thing is, because this speed of B is different from the speed of B at this time. Okay, so let me call this instant of time t prime naught. Okay, at time t prime naught in frame S prime, both B and A have the same velocity. Okay, that is these 2 points. But at this earlier instant of time, B had a smaller velocity. Okay, as measured in the frame S prime. Which means if I switch to the frame S, okay, which way does B appear to be going at the instant t is equal to 0?
Opposite to A.
Yeah, B will appear to be going in the negative x direction, because if I convert this velocity into the reference frame of A, okay, this speed is smaller than the speed of A, okay, and therefore it will appear to be going in the opposite direction. Okay, so in fact, B will not appear to be at rest with respect to this observer A. Okay, so if I go into the instantaneous rest frame of A, B does not appear to be at rest. Okay, so this is something quite counterintuitive, because this is something that doesn't happen in Galilean relativity. Okay, because there's an absolute time. Okay, there's an absolute time, and therefore if B and A in one reference frame are measured to have the same velocity, if I go into a different reference frame in which A is at rest, then you would say that since time is absolute, okay, A and B in that reference frame also have the same velocity, which is 0. Okay. What is unique in special relativity is that time is not absolute, so that when I go into the reference frame of A, I really need to locate where B is at the same instant of time in that reference frame. And since simultaneity is relative, okay, this instant of time is not simultaneous with this in the reference frame S. Okay, although they are simultaneous in reference frame S prime. and therefore A and B do not have the same velocity in the frame S. Okay. So what this means, okay, so this is the problem that I said. So they are not simultaneously at rest with respect to each other as seen in their individual MCRFs. Okay, so if you go to any one's individual MCRF, you will find that the other observers are not at rest with respect to that observer. Okay, and this is because of exactly what we just discussed. Events which are simultaneous in frame S are not simultaneous in frame S prime. So if they have simultaneously the same velocity in frame S prime, and their velocities are constantly changing, okay, in frame S prime, then in frame S, this instant of time where they have the same velocities is not simultaneous, okay? And so in the frame S, this will have, let's say, speed 0, because now you're in the rest frame of this object A. And B, you have to locate it at some earlier instant of time in frame S prime, where it had a different speed V prime. And I transform V prime to this frame V, okay? And so something like this. 1 minus V prime V over C square. Okay, and since V prime and V are not the same because the particle is changing its speed, okay, this new velocity of B as measured in the frame S is non-zero. Okay, so that is the particle B is not at rest in the rest frame of A. Okay, so so here's an issue. Okay, so you cannot have both of the following conditions satisfied for a family of observers in special relativity. Okay, so what are these conditions? So the conditions are that you cannot have observers who have a common rest frame. Okay, that is a common rest frame in which they maintain a fixed distance from each other. Okay, this is not possible at the same time as having observers who have the same constant acceleration in their rest frame. Okay, so here we had observers who satisfied condition B. You had a bunch of observers who had the same constant acceleration in their rest frames. Okay, however, their rest frames or their momentarily co-moving rest frames are not common MCRFs. Okay, that is, one observer's rest frame is not the rest frame of another observer at the same instant of time. Okay, it might be the rest frame of the other observer at a different instant of time. Okay, but they cannot be simultaneously at rest. So there is no common rest frame in which they maintain a fixed distance from each other. Okay, so so now what we would like to do, okay, is have a different class of observers. Okay, so we'll prefer to select observers that satisfy criteria A. Okay, that is, we want observers who have a common rest frame. Okay, all these observers should be at rest with respect to each other, so that if you go into anyone's rest frame, all the other observers appear to be at rest. Okay, that's what you would think of as a standard set of coordinates for an accelerating reference frame. Okay, so you want all the other observers to appear to be at rest with respect to any one accelerating observer, and you want all these other observers to have a fixed distance, okay, from you, so that you can use the distance between each observer, any two observers, as a distance measure, okay, or a coordinate measure of length in this accelerated reference frame. Okay. However, if you satisfy criteria A, you cannot simultaneously satisfy criteria B. That is, all these observers, okay, all these accelerating observers cannot simultaneously have the same common acceleration, constant common acceleration in their rest frame. Okay. So we will choose observers that have a fixed distance between them, okay, which can be used as a spatial distance measure. And so we'll have some distance which will denote as xi, okay, between each observer. And the parameter xi will uniquely label each observer, okay, and it corresponds to the distance between any two observers. And all these observers are at rest with respect to each other as measured in anyone's rest frame. Okay, and so they maintain this fixed distance xi between them as seen in anyone's rest frame. Okay. However, for the second criteria, what you can do is it is possible to find observers with constant acceleration. So each of these observers can have constant acceleration. However, those accelerations will be different constants for each observer. Okay, that is, each observer has an acceleration a, but this acceleration a depends on where they are. Okay, so it's a constant acceleration if your xi coordinate is fixed. Okay, so we'll see explicitly how to construct this. So in their common, and all these observers will then have a common rest frame. Okay, and in their common rest frame, they will have this, each one will have a constant acceleration, except each one's acceleration will be slightly different from the others. Okay. So this family of observers that we'll construct now, okay, are a very important class of observers in special relativity, and they're called Rindler observers. Okay, so these Rindler observers are as close as you can get to a family of accelerating observers in special relativity. So that's why it's important to construct this family of observers. Okay. Any questions about this? I'll now derive explicitly what these Rindler observers look like, so you'll actually see what I mean by the words I just said. Okay, but if you have any questions, feel free to ask at this time. Yeah, go ahead, Tosh.
Sir, in the first case, when the accelerations were all same, but the distance was like some difference was some x naught. But even in that case, only at one instant of time we can still say that like that tau equal to 0 corresponding to this x primed axis, because along this axis when they are all this time axis will be parallel. So for that instant only they'll have same, they'll say that all are separated by the same distance.
That's right. So in fact, as if as you correctly pointed out, okay, if I'm in the frame S prime, they maintain the common fixed distance. Okay, whatever this distance is, delta x naught. But if we go into the frame of A, okay, then first of all, B is not at rest, and secondly, the distance to B, okay, will be some length contracted distance, which is definitely not delta x naught. Okay, and in fact, it will change as A moves. Okay, the distance between A and B, as measured in the rest frame of A, will go on changing as A moves. Okay, so the distance between these two observers itself will go on changing. You're absolutely right about that. More questions?
So the family of observers that we are defining here, is it frame dependent?
Is it frame dependent?
Like,
Well, their trajectories, we are trying to describe the trajectories of all these observers in some inertial frame. Okay, but eventually when we switch over to these observers, we'll use, for example, xi as the distance measure in that accelerated frame, because now this parameterizes a distance between these accelerated observers. Okay, and we'll see that there's a way to define the time, a common time coordinate for all those observers also.
so let's say if we had had one of the observer already chosen in their frame, in their rest frame,
Yeah.
how do we find the S prime frame where all the observers will be at delta x naught?
That will not be an inertial frame. It's not. The point is that it's an accelerated frame of reference. So what you've learned in STR cannot describe that.
Okay.
Right, because these are accelerated observers. So one way to describe these accelerated observers is to talk about going to their MCRFs, because their MCRFs are an inertial frame, right? But what we want to do is try to describe an accelerated frame of reference without reference to a particular inertial frame, which only describes some observers at some instant of time.
Okay.
Okay, so we want to go to a genuinely accelerated frame of reference. Okay, as opposed to snapshots of inertial frames as the accelerated objects are moving. Okay, so let's construct these Rindler observers. Okay, so let me just write out the basic idea here. Okay, so so the basic idea will be, I won't construct them from first principles. I'll just write down the answer and then I'll tell you how this answer gives us what we want. Okay. So the idea is, let's consider this family of trajectories. Okay. Ct prime. Okay. So this again is measured in frame S prime. Ct prime is, instead of just c square by a, okay, I've added a plus xi over here. Okay. Times sine hyperbolic of a tau over c. And x prime is c square by a plus xi times cos of a tau over c. Okay, so this I claim that this is the family of observers, and this family of observers is parameterized by xi. Okay, so for different xi, I get different observers. Okay, so let's see how this works. Okay, so first of all, what is the trajectory described by the set of equations for a fixed value of xi? Okay, so what we'll see is that you get Ct prime square minus x prime square is again c square by a plus xi whole square. Okay, again, this is basically just taking cos square minus sin square. Okay, maybe I made a sign mistake here. Maybe this is minus and this is plus. Okay, but if you see compared to before, if I set xi is equal to 0, I get back my original accelerated observer. Okay, so a couple of things now is that effectively, okay, what this looks like is, so we'll see what this looks like. Okay, so just give me a second. So this is again a hyperbola. Okay, so this trajectory is again a hyperbola. Okay, again, the asymptotes of the hyperbola are exactly the same. So the asymptotes of the hyperbola are Ct prime minus x prime, and these asymptotes are the same for every value of xi. Okay, so each observer has the same asymptotes, as opposed to the previous set of observers that we were considering, who all had different asymptotes. So now basically we're going to see that all these observers, okay, each one of them, okay, has a trajectory which is like this hyperbola, and all these hyperbolas have exactly the same asymptotes. Okay, which means that these, since they all have the same asymptotes, they don't extend into this region. Okay, over here, these observers only exist in this this sort of quadrant, okay, of space-time, okay, which is this region of space-time. Okay, so all observers only exist in this region of space-time, and the family of observers, okay, each one of them is parameterized by a different value of xi. Okay, and their intersection with the x-axis, again, it's easy to guess because c square by a has now been replaced by c square by a plus xi. Okay, at least in this equation for the hyperbola. Okay, so their intercept with the x-axis will be c square by a plus xi. Okay, and now let's see. I have also drawn these as sort of, this hyperbola is more curved than this hyperbola, which is more curved than this hyperbola, and so on. Okay, and all these hyperbolas extending all the way arbitrarily up till here, okay, all have the same asymptotes. Okay, so let's see how this works. So let's try to find for any one of these observers, which is who are parameterized by a particular value of xi, what is their velocity. So in the frame S prime. Okay, so their velocity is dx prime by dt prime, which is again dx prime will give you sine hyperbolic of a tau. Again, I'm keeping xi fixed, so I can just think of it as a one parameter family, one parameter curve, which is parameterized by tau. And so the velocity will be exactly the same. It will be c tan hyperbolic a tau over c. Okay, that's the velocity of any one of these observers. Okay, and the other thing that you can see is if I want to relate this, okay, to my old trajectories, okay, I can instead think of this as this c square by a plus xi. Okay, I can write it as, okay, so I'll write it like this. So c square by a, okay, so I had c square by a plus xi, and now I'll rewrite it as, I'll pull out the c square by a common, and I'll write it as 1 plus a xi over c square. Okay, so so this is that prefactor, okay, times sine hyperbolic of a tau over c, and similarly for x prime, we'll write it as c square into 1 plus a xi over c square by a times cos of a tau over c. Okay, and now what you can do is you can define for each observer who has a different value of xi, you can define an effective acceleration for that observer, a of xi, which is a definition, as A divided by 1 plus A xi over C square. Okay. A divided by 1 plus A xi over C square. Okay. So that effectively Ct prime now, this prefactor is C square divided by this new A, okay, A of xi. Okay, where A of xi is the acceleration of that observer. Okay, because now you see that this is in the same form, okay, as the acceleration that we, the trajectory that we had for an accelerated observer. It's C square over A. Now the only thing that we have to do is the A inside this sine hyperbolic or this cos hyperbolic has to be also replaced by this A of xi. Okay, and when we do that, what we get is we can write it as again A of xi. A can be written as A of xi into 1 plus A xi over C square. So it's A of xi into 1 plus A xi over C square times tau by C. Okay, and similarly, x prime is C square over A xi cos A xi times 1 plus A xi over C square tau by C. Okay. Any questions here about the mathematical step? Okay, all I did was replace the A's inside this by A of xi. Okay, where A of xi is this quantity. Okay, and now if I compare this with the equations that I had before for that accelerating observer, you'll see something interesting. Okay, so previously the equations that I had were C square by A times sine hyperbolic A tau by C, and x prime is C square by A cos A tau by C. Now tau, you can think of it as a parameter of the trajectory, but we saw that for this particular trajectory, it was also something special. Tau actually was the proper time associated with that trajectory. Okay. Now what we can do is we can define for each xi observer, we can define tau prime as 1 plus A xi over C square times tau. Okay, and you define this. So if we take the acceleration of the xith observer to be A xi is A over 1 plus A xi over C square, and you define the proper time tau prime as 1 plus A xi over C square times tau, then effectively this is C square over A xi times sine hyperbolic of A xi times tau prime by C. Okay, and similarly this is also tau prime by C. So what this has done is it's cast the trajectories for the xith observer. Okay, each observer is parameterized by parameter xi. For the xith observer, it's cast them in the same form as the trajectory that we had before. Okay, the only difference is the acceleration is A over 1 plus A xi over C square, and the proper time for the xith observer. Sorry, can you hear me? I got disconnected for a second.
Yeah, we can hear you.
The proper time for the xith observer is 1 plus A xi over C square times tau. Okay, so for each observer xi, their proper time is not tau, but rather it is tau prime, and this tau prime is different for the xith observer. Okay. So let's see mathematically what this translates into. Okay. So let's consider two observers. Okay. Yeah. Sorry. Go ahead, Sadhnik.
Yeah. So is it actually correct to interpret this as the acceleration of the observers, because we are dealing with a scaled version of proper time?
As we'll see, this is the correct proper time for each observer. Okay, tau prime is actually the correct proper time for each observer, and because for a given observer, okay, their trajectory is now now this, right? And this is tau prime. Okay, and as we've seen, once I write the equations in this form, tau prime is actually the correct proper time, okay, for the xith observer. Okay, we can see that explicitly also. We'll work it out explicitly. Okay, that tau prime is the correct proper time for the xith observer. That's also easy to see, right? The correct proper time is dt prime square minus dx prime square, and we'll see that this is equal to c squared d tau prime square. Okay, so for the xith observer, this is what you will find.
Oh, okay, got it.
Right. Okay, so if you consider two observers, one of them, let's for simplicity take them to have a xi coordinate which is 0. Let's call this observer A, and let's take another observer to have a xi coordinate which is xi. Okay, we'll call this observer B. Now, observer 1 has proper time tau. That's as we'd seen before. If xi is 0, then their proper time is tau. And at some time t prime, okay, which can be related to tau, the observer A has a velocity v prime, which we've seen before is c tan hyperbolic a tau over c. Okay, that is, let's say if I pick one observer, okay, this is A, or let's call this A, and let's call this B. So this observer has a velocity here, which is tan hyperbolic a tau by c. Okay. And now let's ask this question. So now if we are in the rest frame of A, okay, now we're in the rest frame of A, and what we want to know is if we take this observer B, okay, who effectively has a different acceleration. Okay, so it's exactly like the same hyperbola with the same asymptotes, except its curvature and its intercept are different. Okay, again, the intercept has to do with this A of xi. Okay, and the curvature also has to do with A of xi. Okay, so basically, the curvature of this hyperbola has to do with this parameter, c square by a plus xi whole square. Okay, and if xi is larger, this parameter is larger. Okay, and this curvature is smaller. Okay, this curvature becomes smaller. So as I go to large xi, okay, I'm going to hyperbolas which are further over here. Okay, and as I go to small xi, I'm going over here. And in fact, there's a very special case where if I go to the limit where xi is equal to minus c square by a, okay, then what I get is the limit where I just get these two asymptotes. Okay, or in other words, these hyperbolas basically just become their asymptote. So I'm getting narrower and narrower hyperbola. Still, effectively, this hyperbola pinches off and becomes just these two light rays. Okay, and that happens at a finite value of xi, which is minus c square by a. Okay, so xi extends from minus c square by a on the left, okay, which is basically where it reaches these two asymptotes, to all the way to xi is infinity, which is like basically a hyperbola, which is kind of like at infinity and asymptotically approaching these light rays. Okay. Okay, so now what you can do is now we can ask for this family of observers. Suppose we take observer A, okay, and we'll take another observer B, a generic observer who has some coordinate xi, okay, which is non-zero, and we'll ask if we are in the rest frame of A, okay, two questions. One, what is the distance to B? And the second question is, what is the velocity of B? Okay, where B is any generic xi observer. Okay, and what we'll find is two things. One is the velocity of B will be 0. Okay, it doesn't matter which of these observers you take, they will all have all be at rest with respect to each other. Whereas if you go into the rest frame of any one observer, all the other observers will simultaneously be at rest. And the distance to B will just be xi. Okay, so xi will parameterize the distance between these observers in their common rest frame. Okay, and when I talk about rest frame, I'm talking about going to the MCRF. Okay, the momentarily co-moving rest frame, which is an inertial frame of reference. Okay, so the first thing you need to do again is you take the curve of A. Okay, you draw the tangent to that. That is your t prime axis, or that's the sorry, I'm switch notations here, but let me just call this the t axis and this is the x axis. Okay, and what I want to do is I now want to locate where B is. Okay, at the instant t is equal to 0, so I would draw this line and locate where B is. Okay, so this is B over here. And now what I want to do is find out what is the speed of B at this instant of time. Okay, and the claim is both hyperbolas, okay, will have the same tangent, okay, at these different points. And because they have the same tangent at these different points, B will basically be at rest with respect to A. Okay, B and A will have the same velocity. In particular, if I go into the rest frame of A, B will have zero velocity. Okay, and this corresponds to a simultaneous time in the rest frame of A. Okay, so you see that this is a rather subtle construction, right, of these family of observers, so that A and B in their common rest frame are at rest with respect to each other. Okay, and here B was any generic Xi observer, so this would be true for any observer that I construct. Okay, this observer I would locate them at this time, and they would be at rest with respect to the observer at A. Okay, and they would maintain a fixed distance. So if B has a coordinate Xi, the distance between A and B would be let's say Xi B, and the distance between these two would be, if this is some third observer Xi, this distance would be Xi C. Okay, and so there is a common rest frame, common MCRF for all these observers, and all these observers maintain a fixed distance. So if I have Xi C, Xi B, and let's Xi A, which we're taking to be 0, the distance between them is fixed. Okay, it's delta Xi. Okay, between these two observers in their common rest frame. Okay, so let's see how this works out. Okay, so what we'll do is, sorry, I just switched notation when making this note. So I'd call this T prime and X prime. So the rest frame of A here I'm calling S prime, and the original inertial frame I'm calling S. Okay, so the prime coordinates are with respect to the MCRF of A. Okay, so now basically what I want to do is I want to switch from the coordinates of S, which are X and T coordinates, okay, to a frame T prime, which is the rest frame of A. Okay, and at some instant of time as measured in the frame S. Okay, so I'll take at this instant of time as measured in the frame S, I will assume that that A has a velocity which is tan hyperbolic A tau by C. Okay, so what I want to do now is transform. So this is just a standard Lorentz transformation of the coordinates of B, okay, of the coordinates of B into the rest frame of A. Okay, so I make a Lorentz boost by a parameter beta, where beta is the velocity of A. Okay, so I'm transforming the coordinates of B into the rest frame of A. So the velocity that I'm using is the velocity of A. Okay, and I'm using that to get the coordinates of B, okay, in that rest frame. Okay, and so when I do this, okay, so first I need to know what are the coordinates of B in the original frame, and that I already told you. XB is C squared by A plus Xi, because I assume that B had a coordinate Xi. Cosh A tau over C. TB is C squared by A plus Xi, sine hyperbolic A tau over C. So I plug in this value of beta. Okay, so gamma depends on beta, and I plug in this value of XB and TB in here. Okay, so maybe I won't work it out in detail, but first thing that you'll get is that first of all TB prime will be 0. Okay, which indicates that and by my coordinate choice I assume that TA prime was 0. So which means that I've located B sorry, I've located B at the same instant. So if I fix tau to be common for A and B, okay, that is I fix a common tau for A and B, okay, then what I will find is that so this is tau, okay, which parameterizes the location of A, and this is tau which parameterizes the location of B. Okay, and what I will find is that for the common value of tau, okay, A and B are at rest with respect to each other. Sorry, yeah, Utkarsh?
Yeah, can you explain again where we have used Lorentz boost? What are we trying to do?
So what I'm trying to do is I'm trying to find the coordinates of B, okay, in the rest frame of A, in the MCRF of A.
Okay.
Okay, so the MCRF of A is some frame S. okay, S prime or S, okay, S prime is what I'm calling it here, and I want to go into this reference frame, and I want to locate the coordinates of B in this reference frame. Okay, at the same instant of time, at which I've located A.
And we are using the old coordinates of B in S frame. Hence that beta is equal to the velocity of A.
Yeah, so I'm going from frame S to frame S prime.
Yeah.
And they're related by the velocity of A.
Yeah.
Right, which is this beta. Okay. So when I make this transformation, two things. I will find that first of all that that if I locate B at the same tau, okay, so tau we don't know what it is. It's some parameter which parameterizes the trajectory. But if I locate B at the same tau, then I will find, okay, that B is has TB prime is equal to 0, which its time coordinate in the frame S prime is also 0, which means this is so this would correspond to that simultaneous point. Okay, I mean I've drawn it pictorially, okay, but you can work this out. Okay, so this would correspond to the same instant of time T prime is equal to 0. Okay, and specifically it's this space-time point is what I'm labeling as B. Okay, and that point has T prime is equal to 0, and this point also has T prime is equal to 0. Okay, so these are simultaneous. And now I want to ask at that simultaneous point, what is the velocity of B? Okay, so that is I want to check that B is at rest with respect to A at this common instant of time as measured in the frame S prime. Okay, so what I'll find is that XB prime. Okay, let me not walk through the math. Okay, I'll leave it in the notes for you to check. But I hope the physical picture is clear. So okay, so basically this point and this point will have the same tau value. Okay, but remember tau is not the proper time of each observer. Tau is only the correct proper time for this observer. Each observer has a different tau prime, okay, which is related to tau. And if I locate these observers at a common tau, okay, then I will find that all these observers have the same value of all these observers have the same value of time, okay, as measured in the MCRF of any one of them. So that means these are all simultaneous space-time points as measured in any one's MCRF. And the second thing is that the distance between them, another thing you can check is it remains fixed at xi. Okay, or so this distance will be xi a minus xi b. This distance will be xi b minus xi c. Okay, so I'll leave this as a homework exercise, or you can check the math through the notes. Okay. So these are the two things that you can check. One is that B is at rest with respect to A in the MCRF of A. And the second is that the distance between A and B in the MCRF remains fixed. Okay, it remains xi. Okay, so that is, we see that criteria A is satisfied. Okay, that is, there is a common frame in which all the observers are So now let me just draw another diagram so you can see it here. Sorry. So these are the light rays, which are the asymptotes. Okay, this is X and this is T. This is our original observer. Okay, and now we're drawing a family of observers which are also hyperbolas. But as I get closer to this point, okay, these hyperbolas become sharper. Okay, these hyperbolas don't intersect with each other. Okay, they don't intersect with each other. Sorry, they all asymptote to the same. And each one is parameterized by a xi coordinate. Okay, so xi is equal to 0 will intersect the x-axis at c square by a. Xi is equal to minus c square by a will intersect here, and that's the limit of this limiting hyperbola. And then as I go to large xi goes to infinity, I get hyperbolas which are further and further away. Okay, but they have the same asymptotes. And basically the observer with a particular value of xi has an acceleration a xi, which is a over 1 plus a xi over c square. Okay, so what you can see is that as xi becomes large, that is as I go to this observer, a xi goes to 0. Okay, so this observer, basically the limiting observer to the far right, has 0 acceleration in their MCRF. Okay, versus as I go to the left, okay, as xi goes to minus c square by a, the acceleration a xi, okay, for xi goes to minus c square by a, the acceleration goes to infinity. Okay, why is it infinite? Because you can see that you have a speed c, okay, towards the left, and then suddenly you turn and you have a speed c towards the right. Okay, so you basically change velocity by 2c in a time t goes to 0. Okay, so your acceleration is infinite. Okay, so this is the limiting case of that infinite acceleration observer. Okay, so observers with smaller xi have to so the other thing is, you see that as xi gets smaller, okay, your accelerations are getting larger. As xi gets larger, your accelerations are getting smaller. Okay, so now all of these observers in their common rest frame are maintaining. So the common rest frame, if I pick out all these space-time points, these space-time points have are at rest with respect to each other. So if I go into anyone's rest frame, I will find that these are the simultaneous points. Okay, these are simultaneous points, and they're all at rest with respect to each other. That is, the velocity here is the same as the velocity here, which is the same as the velocity here, which is the same as the velocity here. And that's easy to understand because this object is accelerating faster. Okay, and this object is accelerating slower, as seen in this frame S or S prime S. This object will have the same speed as this object at a later instant of time. Okay, and this object will have the same speed as these two at an even later instant of time, and this object will have the same speed as all of these at an even later instant of time. Okay. The same speed, but at different instants of time as measured in the frame S. But in their common rest frame, they all have 0 speed at the same time. Okay, so they all have a common MCRF. Okay, so that's the key feature. There's a common MCRF. Okay, for all these observers. And the other thing that you see is they all maintain the same distance between each other. So the distance delta xi between any two observers is fixed. Okay, in their common MCRF, that doesn't change. And so what that means is, as seen in the frame S, in order to preserve the distance delta xi between any two observers A and B, you see that observer B has to accelerate much harder to keep up with observer A. Okay, and to preserve that distance delta xi between them. So B has to accelerate harder, C has to accelerate even harder, and D has to accelerate even harder to try to keep up with these other observers and maintain the same common distance between them in their MCRF. Okay, so these are some peculiar features of accelerating observers in special relativity. Okay, so let me just summarize the basic points. Okay, so in STR, you can only have observers with a common MCRF and fixed distance between them with constant accelerations only if each accelerates with a slightly different acceleration. Okay, that is, each of these observers has to have a slightly different acceleration, more acceleration as I go this way, less acceleration as I go this way. And in fact, there's a particular observer with infinite acceleration who barely manages to keep up. Okay, now what happens if I try to go to an observer with basically what this means is any observer who is beyond this point, no matter how hard they accelerate, they will never be able to keep up and maintain a common fixed distance to these other observers. Okay. So this family of observers, which I wrote down the equations for, okay, these are called Rindler observers. So they're a family of observers which are parameterized by this parameter xi and another parameter tau. Okay, tau is not the proper time for each observer. Rather, tau prime is the proper time for each observer. Okay, where tau prime is 1 plus a xi over c square times tau. Okay, So tau you can only think of as a parameter that describes the trajectory. It's not the proper time of each observer. Okay. And the other thing about these trajectories are there's a range of xi values, okay, which are allowed for these observers, which is xi goes from minus c squared by a to infinity, and tau goes from minus infinity to infinity. Okay. So that's it. Now there's a simple way of rewriting this, okay, where I change my parameters. Okay, so I can change my parameters to, I can define c squared by a plus xi as rho and a tau over c as eta. Okay, so when I do this, ct is rho sinh eta, describes my observers, and x is rho cos eta, describes the x coordinate. Okay, so this is rho cos eta and rho sinh eta. Okay, and what is the range of the rho parameter? Rho is c squared by a plus xi, so that goes from 0 to infinity, and eta goes from minus infinity to infinity. Eta is just a tau by c. Okay, eta is the rapidity of that special observer with xi is equal to 0. Okay, so rho is like your, in some sense, rho you can think of as like your spatial coordinate, okay, or it's like xi. It's a measure of distance between any two of these accelerating observers. Okay, so any two of these Rindler observers will see a constant distance xi between them in their MCRF, or delta rho between them in their MCRF. Okay, and eta is in some sense like a time-like coordinate. Okay, strictly speaking, it's proportional to the proper time of only one of these observers. For a different observer, I would have to scale tau to tau prime. Okay, and therefore I would have to scale eta by eta into 1 plus a xi over c square, or equivalently I would have to scale it as eta times rho times times c square by a. Okay, this would be like the time coordinate tau prime, okay, of the xith observer, okay, or the rhoth observer. Okay, but in some sense, eta is like a common time that I can think of for all these observers. Okay, so rho is like a space coordinate, and tau is like, eta is like a time coordinate for all these observers. And if I specify a particular rho, I'm specifying a particular Rindler observer. If I specify eta, I'm specifying what time I'm talking on in the trajectory I'm talking about them. Okay, so, and these Rindler observers are, because of all the constraints that I told you about earlier, right? You cannot have constant acceleration in frame S prime, so you must have constant acceleration. It's only possible to have constant acceleration in the MCRF. And secondly, those two constraints, if I try to take a family of observers, and if I want to maintain a common fixed distance between them, then the only way that can happen is if all these observers have different accelerations in their MCRFs. Okay, so these Rindler observers are as close as you can get to uniformly accelerated reference frames in special relativity. Okay, and because we discussed the equivalence between uniformly accelerated reference frames and uniform gravitational fields, okay, this understanding Rindler observers is really going to help us gain an intuition for the equivalence principle as applied to special relativity. Okay, so I'm going to continue to talk about this. So if there are any questions here, otherwise we'll move on to discussing more about Rindler observers.
Hello.
Yeah.
So here eta is also dependent upon rho, right? Because xi is coming. If eta prime, if we write eta prime, then it will depend upon rho as well.
You mean instead of tau prime?
Yeah. So like from tau prime we go to eta prime. We define eta prime, and in eta prime the xi can be written as rho, function of rho. Yeah.
Yeah, you could do that. Okay, and then what you do is then you redefine these coordinates as you can do this. Okay, and then you can just write it as ct is rho sinh eta prime, roughly up to constant. It's eta prime by rho, because I just want to replace this by eta, and then there's some factors of c squared by a. Okay, so I can write it like this also. So I could have used eta prime also. You're right.
Okay.
Okay, but you can also work with eta. Okay, there's nothing wrong with either of these choices. Okay. In fact, we'll see that this is kind of like the very heart of the idea of coordinate invariance. Okay, it doesn't matter what choice of coordinates you use for the accelerating observers. Okay.
Also, one
Yeah.
more thing.
Yeah, go ahead.
So for common MCRF, we have to choose one particle for which the tau will be the proper time for that particle, right? Like this is
Yes.
our choice. Okay. And for the rest of them, we have to use tau prime for the proper time.
Yeah, but you don't really have to worry about tau, right? It's just a parameter that describes some point in the trajectory. Okay. The point is you can always go to an MCRF, right? And in that MCRF, you can find that the other observers are at rest.
Yeah.
Okay. Tau has a special interpretation for one observer.
Yeah.
As the proper time of that observer. Okay. In general, tau prime will have the correct interpretation as the proper time for the xith observer. Okay, or equivalently eta prime. Okay, so let me just okay, the plan is to talk more about these Rindler observers. Okay, so so now let's continue this discussion of Rindler observers, and let's ask. Okay, so now in the simplified way of writing it, it actually becomes much easier to see what these Rindler observers are. Okay, so T is rho sin theta, X is rho cos theta, and for different rho, I get different trajectories. So these are trajectories with constant rho. Okay, that is, I have a different Rindler observer for a given value of rho. So that is, I get, if I change rho, I'm on a line of, sorry, I'm on a hyperbola. Okay, so as I start from eta is minus infinity, I'm at one end of this hyperbola, and as I go to eta is plus infinity, I'm at the other end of the hyperbola. And if I take a fixed value of eta, okay, then that fixed value of eta, and if I just look at different rows, okay, that fixed value of eta will correspond to different points along a line passing through the origin. Okay, how do you see that? Well, sorry. So T by X is tan hyperbolic. Sorry, X by T by X is 1 over. Sorry, T by X is tan hyperbolic eta. Okay, so so basically the slope of this line, okay, is tan hyperbolic of eta. So for different eta, I get different lines passing through the origin. Okay, so eta describes all these different points. Okay, and you can check that all these different points, if I go to the rest frame of any one of these observers on one of these hyperbolas, the other points would be appear to be at rest. Okay, with respect to this observer. If I take all these space-time points, the observer on the pink hyperbola would appear to be at rest with respect to this white observer on the white hyperbola at these common space-time points. Okay, which appear to be simultaneous. Okay. Now, this entire region of space-time, if you try to send a signal, okay, even at the speed of light to any of these observers, none of these observers will be able to receive that signal. Okay, none of these observers will be able to receive the signal from this region of space-time. So this is called a Rindler horizon. Okay, it's a common horizon for all the Rindler observers. Okay, and yeah, and I've drawn these points 1, 2, 3, and just to tell you that all the Rindler observers will have the same velocity for a common eta. Okay. So they have a common MCRF. In the common MCRF, Rindler observers have coordinates ρ1 and ρ2. And in their common MCRF, they maintain this fixed distance ρ1 minus ρ2. So even as eta changes, so there are different points on the trajectories, their distance ρ1 minus ρ2 between them in their rest frame will be fixed. Okay, it'll be just ρ1 minus ρ2. So now this entire region of space-time where these Rindler observers exist, okay, this is called a Rindler wedge. Okay, it's like a wedge in space-time. Now, instead of trying to describe the space-time coordinates of this region by going to any particular Rindler observer's rest frame and then having to change that rest frame, what you can do is you can take a particular point in this space-time. Okay, so sorry, let me just erase these. You can take any particular point in this space-time, okay, and there's only one Rindler observer who passes through that point in space-time. Okay, only one of these Rindler observers passes through that point. So you can describe the coordinates of this point instead of describing them by these inertial coordinates, that is x and t, in the frame S, or the initial coordinates of some other rest frame, okay, of any particular Rindler observer. Instead of describing them by inertial coordinates, what you can instead do is describe them by what are called Rindler coordinates. Okay, that is, you can describe this particular space-time point by the rho of the Rindler observer who passes through this point. Okay, and you can describe this point by the eta at which corresponds to the time or the proper time at which this Rindler observer passes through that point. Okay, so each point in this Rindler wedge is uniquely labeled by a value of rho and eta. Okay, so if I consider all space-time points in the Rindler wedge, instead of describing them the coordinates using the orthogonal coordinates in the inertial frame S, you can switch to Rindler coordinates. That is, you can describe them by a rho and an eta. Okay, and this is really now analogous to defining a uniformly accelerated reference frame in Galilean relativity. Okay, because a coordinate rho tells me that for these Rindler observers, so imagine that you're one of these Rindler observers who's accelerating, and your friend is another one of these Rindler observers who's accelerating. According to you, okay, your friend is always in your rest frame, this friend is always at a fixed distance from you. Okay, so using a coordinate rho as a distance measure makes sense in your reference frame, right? And similarly, using eta as some kind of measure of time coordinate also makes sense in your reference frame. Okay, although this is not the proper time for all the Rindler observers. Okay, it's the proper time for only one of the Rindler observers. Okay, so it's this defines what is called a Rindler frame. Okay, that is, you define the space-time points instead of describing them by inertial coordinates, you describe them by so-called Rindler coordinates. Okay, that is, you describe them by a rho and an eta value. Okay, so just to go back to the example that we were doing earlier. Okay, so imagine that you're in an elevator. Okay, and this is your plus x direction. You have two apples with you. You're in an inertial frame. The apples don't fall. Okay, so you maintain a constant x. Now let's imagine that you're in an accelerated frame of reference. So this is the positive x direction. You're accelerated upwards with an acceleration a. Okay, and now what would you see? Okay, in this accelerated frame? Well, if initially you're like, let's say in the middle of the elevator, you're not yet touching the floor of the elevator will come up and hit you. Okay, and similarly the floor of the elevator will come up and hit the apples. Okay, within this accelerated frame, it would seem like the apples are falling downwards, and again that you are falling downwards, and your internal organs are falling downwards. Okay, that's because you are inertial and the frame is accelerating. Okay, so the analog of that is, if I study an inertial observer, so an inertial observer would be, let's say, in the original frame S. Okay, the inertial observer would, let's say, be here, and let's suppose they maintain a constant x coordinate in their own reference in the frame S. So they would just follow this kind of trajectory. They would just go like this. Okay, now according to the accelerated reference frame, this inertial observer, what are they doing? Well, their rho coordinate, okay, at later and later instance of eta, as eta gets larger and larger, this is a line of constant eta, this is a line of constant eta, this is a line of constant eta. So as their eta coordinate gets larger, what is happening to their rho coordinate? So this is the rho coordinate here. This is the row coordinate here, this is the row coordinate here, this is the row coordinate here. What is happening to the row coordinate? Is it getting larger or smaller?
Larger.
So remember that rho is c squared by a plus xi. Larger xi is this way. Okay, smaller xi is this way. So this limiting hyperbola is rho is equal to 0. The faraway hyperbola is rho is infinity. So as you're going upwards, you're crossing all these hyperbolas. So you're going from a larger rho to a smaller rho. Okay. Eventually, you will get to the rho is equal to 0 hyperbola, and eventually you will even cross that hyperbola. Okay. Because in the inertial reference frame, nothing special is going on. Okay. You're just at the same x and you're just crossing t. It's the Rindler observers who are accelerating, and therefore you cannot communicate with them once you cross this Rindler horizon. Okay. So as time passes, okay, it would appear that your rho coordinate is decreasing, which is like in the accelerated reference frame, the inertial objects appear to have a decreasing x coordinate, okay, if the acceleration is in the positive x direction. So in this accelerated reference frame, the acceleration of these Rindler observers is to the right. Okay, of course, they have different accelerations in STR. And the inertial observer, which is like that apple, okay, which is that apple itself maintains a constant x coordinate in the inertial frame. Okay, but according to these accelerated observers, the rho coordinate of this apple is going on decreasing. Okay, but that's because secretly the lift itself is accelerating upwards. Okay, and therefore the apple appears to be accelerating in the opposite direction. It appears to be accelerating in the opposite direction. Okay. Okay, so now let me just state some properties of these of this Rindler frame. Okay, so one is if you take the distance between any two space-time points in the original inertial frame S. Okay, so ds square was equal to minus c square dt square plus dx square. Okay, this is the space-time distance, which is an invariant for all inertial observers. All inertial observers will agree about this. Okay, and this is the way they measure that space-time distance. Now, if we switch our space-time coordinates to using these Rindler coordinates, that is rho and eta. Okay, we want to ask in terms of rho and eta, if I had points which were at x, t, and x plus dx and t plus dt, if I had these two space-time points, what is the space-time distance between them, which is this, but now as measured in terms of changes in rho and eta. So this point is described by rho eta. This point is described as rho plus d rho, eta plus d eta. Okay, and what you would find is, so I can write out dt. Okay, so dt is, first let me differentiate with respect to rho. So this is sinh eta d rho. Now I'll differentiate with respect to eta. So that's rho cos eta d eta. And similarly, I do the same thing for x. So dx is cos eta d rho plus rho sinh eta d eta. Okay, so I differentiate with respect to eta. And now I square this. So I take dt square and I take dx square. Okay, so actually this is cdt. So I square this, okay, and I take a minus sign and then I add this to dx square. Okay, so what you would get after you do this, okay, so you can simplify this. So this is this square plus this square. Okay, and you can see that the cross terms will cancel out. And what you will get at the end will be something proportional to d eta square, but which will come with a rho square prefactor. Okay, because it's cos hyperbolic square minus sin hyperbolic square will give you 1. So this will have a prefactor of rho square. And the d rho square, okay, will come with a prefactor of 1. Okay, so the invariant distance measure between two space-time points, if you now express it in terms of Rindler coordinates, looks slightly different. Okay, it's not d minus d eta square plus d rho square in these accelerating reference frame. It's minus rho square d eta square plus d rho square. Okay, that is the time-like coordinate comes with an extra factor of rho sitting in front of it. For the rhoth observer, okay, there's an extra d eta. Now, what's the intuition for this? Well, the intuition we've already seen. So let me explain why this factor of rho comes out here. Okay, so first let's consider two observers who have the same eta coordinate, that is d eta is 0. Okay, so you consider two observers at rho and rho plus d rho, but at fixed eta, that is d eta 0. Then for these two observers, we already know that they have a fixed distance between them as measured in their MCRF, and that is a proper length. Okay, that is d rho is the length between them, and this is a Lorentz invariant distance measure. It's the rest frame length between them. Okay, in their common MCRF, it's the rest frame length. So it makes sense that if d eta is 0, this distance measure ds square is d rho square. Okay, but now let's ask a reverse question. So let's take let's take two observers, okay, who are on the same hyperbola. Okay, but one is measured at an earlier instant eta, and the other is at a later instant eta plus d eta. And let's ask, what is the invariant spacetime distance between these two observers? Okay. Now, as we've discussed, the proper time for the rhoth observer is d tau prime, okay, which is a Lorentz invariant quantity. So the proper time between these two is the spacetime distance between them, and that's d tau prime, and that's a Lorentz invariant quantity. Now, as we've discussed, the observers at xi and xi prime, okay, they have different accelerations, and so the proper time d tau prime is now here I fix the value of rho, so I fix the value of xi. So it's so this is a fixed quantity, which is 1 plus a xi over c square times c d tau. Okay, so d tau prime, which is the proper time of the xith observer, okay, is related to d tau, which is the proper time of the observer with xi is equal to 0, times this extra factor, okay, which is xi dependent. So I can write it as this. I can write it as c square by a plus xi times a by a d tau by c. Okay, so this is the proper time, which should give the correct Lorentz invariant distance between these two observers. Okay, so what I can do now is I can write the c square by a plus xi is what I had called rho. Okay, and this a d tau by c is what we had called d eta. So what we see is that the proper distance between these two observers is just rho times d eta. Okay, rho times d eta. So intuitively, you see that when d rho is 0, okay, two observers on the same Rindler trajectory at different instants of time have a proper distance between them, okay, or the proper time between them, which is rho times d eta. And this is different for different Rindler observers. Okay, so if I take one Rindler observer, they have a different rho coordinate, a different Rindler observer has a different rho coordinate. So for the same d eta, okay, their proper distance will be rho times d eta, okay, rather than just d eta. Okay, so is this idea clear? Why this factor of rho comes out here and why there's no factor here?
This looks somewhat, I mean, I see it very analogous to what you would have in like circular polar coordinates in some.
Very good. Yes, indeed. Indeed. This is very analogous to that. I'll show that explicitly. Any other comments or questions? Yeah, in fact, let me just address the point that Anish raised. So Rindler coordinates are like hyperbolic analogs of 2D cylindrical coordinates in Euclidean space. Okay, so just like in Euclidean space, if I take a distance measure between 2 points, let's say x, y, and x plus dx, y plus dx, y plus dy, the distance between them is dx square plus dy square. Okay, or dr square is dx square plus dy square. But I can switch to polar coordinates, and in polar coordinates, I can write x as r cos theta, y as r sin theta. And then the distance measure is dr square plus r square d theta square. Okay, so for theta is constant, for a constant theta, the distance between them is just dr, right? Because I'm just going from r to r plus dr. But as I go for r is constant, if I take r as constant and I just switch thetas, then what I at a fixed r, depending on which r I'm looking at, a fixed d theta corresponds to a slightly bigger arc length. Okay, so it's r times d theta is the distance between 2 points. Okay, so if I'm at this r, I will get r times d theta. And if I'm at this r, I will get r prime times d theta. Okay, and that's a bigger length. Okay, so that invariant distance changes as I change r. The analog here is in 1 plus 1d Minkowski space. The distance measure that we're using is dx square minus dt square. Okay, that is the correct Lorentz invariant distance, which is invariant under rotations as well as boosts. And here the transformation, instead of being through trigonometric functions, is through hyperbolic functions. So x is rho cos theta, t is rho sin theta. These are the hyperbolic Rindler coordinates. Okay, and what we found is that the distance measure is like d rho square minus rho square d eta square. So it's very analogous to how we had r as the radial coordinate. Rho is like a radial hyperbolic coordinate, hyperbolic radial coordinate, and this eta is like a hyperbolic angle. Okay, over here. Okay, so you get minus rho square d eta square. So eta is a constant, gives you a straight line from the origin, as we've seen before. Okay, in the original xt space, and rho is constant, gives you these hyperbolas. Okay, and as you're going further and further out, okay, in so if I want to take 2 points on the same hyperbola, which are d eta separated, depending on which hyperbola I'm on, okay, the invariant distance between these 2 points, if I go this way, the invariant distance increases and it's proportional to rho times d eta. Okay, and if I go this way, that invariant distance decreases because rho is smaller. Okay, so that's the analogy. Okay, and as Anish pointed out. Okay, so let me just say one last thing and then we'll stop. Okay, these null lines, that is x is equal to ct and x is equal to minus ct, which are the asymptotes, you can think of reaching them as eta goes to plus infinity or minus infinity. Okay, so once eta goes to plus infinity or minus infinity, you've reached basically the end of your Rindler coordinates. Okay, now that doesn't mean that space-time has stopped. It just means that the Rindler observers are no longer able to describe these other points. Okay, so these other points are outside the description of this set of observers. What's special about this set of observers is that they can maintain this fixed distances between them in their co-moving rest frame. Okay, and they have a common rest frame. So you can't find other observers who are maintaining a common distance to these other observers who exist in this region of space-time. Okay, which is why you can't extend the Rindler coordinates to include these regions. Okay, so those regions really are outside of the world of these Rindler observers in some sense. Okay, so we'll talk more about this Rindler horizon. So just mark this point. So this is where we'll stop today. Yeah, so I'll just discuss a few more points about these Rindler observers next time, and then we'll take some lessons from this. Okay, we'll take some lessons that we learned from Rindler observers, and we'll see how those lessons translate into describing general relativity. Because as we've seen, the entire point of studying accelerations is that accelerations locally, if I have uniform accelerations, that's equivalent to a uniform gravitational field. And since we're trying to understand gravitational fields combined with special relativity, okay, it's useful to understand what is different about Rindler observers or accelerating observers in special relativity, so that we're not surprised when we encounter similar phenomena in a more general theory, which encompasses general gravitational fields, not necessarily those caused by accelerating, just uniformly accelerating reference frames. Okay, we'll stop here, and if anyone wants to stick around for some discussion on paradoxes in special relativity in the context of this discussion, I'm happy to discuss that, but that's not part of this of this course. Okay. Any questions at this point?
Hello, sir.
Yeah.
So my doubt is not related to the paradoxes. I just wanted to know, like in the last class, you defined those Rindler horizons. You said that these are event horizons, because light from the other region can't reach to the observers in the region enclosed by this. But sir, I think these saying that these are event horizons is not correct, because we know that in Minkowski space there are no event horizons, because I mean the metric doesn't vanishes at any point. The metric doesn't become undefined at any point in the space.
No, okay, so maybe I'll discuss what this means. So I said there's similarities. Maybe I misspoke, but what I mean is that there are similarities between the horizon, very close similarities between the horizon that a Rindler observer sees and the horizon that you would see around a black hole. Okay. Now, the difference is that a black hole has a singularity behind the horizon. Here, there's nothing special behind the horizon. It's just Minkowski space. Okay. It's just ordinary space, Minkowski space time behind the horizon. That's really the main difference between these two horizons. But more or less, otherwise they're the same. The properties, as you cross the horizon, the experience that you have is very similar.
Yes, sir. So, sir, maybe saying like they are more like killing horizons rather than event horizons would be a.
Technically, yes, that is the correct term, but we have not defined that yet.
Yes, sir. Yes.
Any other comments or questions? Okay, so let me just come to these two paradoxes that I wanted to talk to you about. Let's see if I can find it.
Excuse me, sir.
Yeah.
So where do you upload these notes?
I will upload them to Teams. I have not yet uploaded them.
Oh, okay.
Okay, so let me just tell you about these two interesting paradoxes in special relativity that will be really easy to understand in light of the discussion that we had today. Okay, so so here's one thing. So imagine that you have a rocket ship, okay, and two rocket ships which are connected by a string. Okay, so this paradox is called Bell's spaceship paradox. Okay, and now the idea is that both these spaceships accelerate with an acceleration a, the same acceleration a. Okay, and this string is of length L. Okay, so let me see if I can phrase the paradox correctly. So now as they accelerate, okay, they will pick up a velocity v. Okay, and then one argument would be that, okay, then this length would appear to be length contracted. Okay, so that is the length would be shorter as measured in this inertial frame S that we're observing these rockets in. So the length would be shorter. Oops. Okay, and okay, let's assume the rockets are practically point-like. And sorry, so let me just see if I can remember the paradox. Sorry, just give me a second. Yeah. Okay. So the idea is actually that that surprisingly what happens is when this accelerates, okay, what you can show is that this thread will always break. Okay, that is whatever is connecting them will snap. Okay, let me see if I can explain why what the original paradox is though. Yeah, okay, so the paradox is roughly like this, okay? So if this is moving with speed v, they both have the same speed as measured in the reference frame s at any instant of time. Okay, okay, sorry, I can't really paradox, but let me explain what is going on. Okay, so this is analogous to the first set of Rindler accelerated observers that we defined here. So this is x and this is t, and these are two accelerated observers. Okay, who are at so this is like the first class of observers that we had seen, where ct is equal to c squared by a times sine hyperbolic a tau by c, and x is equal to c squared by a cos hyperbolic a tau by c plus x naught. Okay, and what you can see is that these observers, as we discussed earlier, have different asymptotes. Okay, so these are the asymptotes of this observer, and these are the asymptotes of this observer. Okay, so now the thing is, when these two spaceships accelerate, okay, so they have a thread connecting them. So this spaceship accelerates, the other spaceship accelerates. Now, very quickly, what you will see is that this spaceship, right, is outside the Rindler horizon, or this is the Rindler horizon of this observer. And this spaceship, even if it started inside the Rindler horizon, let's say over here, would eventually exit the Rindler horizon, okay, because it has different asymptotes. Okay, so even if it started within the Rindler horizon, this spaceship would exit the Rindler horizon. Okay, so let's assume that they start here together. Okay, so even if they were very close together to begin with, okay, these are the asymptotes of the blue curve. So at some point, this observer would exit the Rindler horizon of the second observer, okay, of the second rocket ship. Okay, so this would be the lagging rocket ship, and this would be the leading rocket ship. Okay, so this leading rocket ship would basically find that light signals from this can no longer reach this observer. So what would happen is, eventually, when you cross this point, okay, is that you need to accelerate with an infinite acceleration to kind of keep up, right? If once you're at the Rindler horizon, you need to accelerate with an infinite acceleration to keep up with this leading rocket ship. Okay, and the fact that you don't have infinite acceleration would mean infinite force, which acts on the object. And if you basically, what it would appear to this observer is that there is an infinite force acting at some point here. Okay, and therefore the string would snap. Okay, so this seems highly counterintuitive, because you would think that if I have two objects which are both accelerating with the same acceleration a, then it should be possible for both of them to continue to maintain the same distance between them. Okay, but as we've seen, these two accelerating observers, if they maintain a fixed distance between them in frame x naught, in their own rest frame, they cannot maintain the common fixed distance between themselves. Okay, because the measurement of the speed of the first rocket ship and the second rocket ship as being simultaneously v is only valid in this inertial frame S. But if I go to the reference frame of any one of these rocket ships, the other rocket ship does not appear to be at rest. Okay, and so in fact, when it crosses the Rindler horizon, it appears that there's an infinite force somewhere on this thread, and therefore the thread will actually snap. Okay, so they cannot actually stay in contact with each other, maintaining this common distance. Okay, the second thing that I wanted to discuss is this pole and barn paradox. Okay, which is basically you have a barn, okay, which has a proper, it has a door, and there's a rod, okay, and this barn has a length L0, and the rod has a length L0. Okay, these are the rest lengths. Okay, and now you have someone standing at the gate, okay, and holding the gate open, and there's someone holding this this rod and running into the barn. Okay, and this person opens the gate when the front of the rod enters. Okay, and they close the gate when the back of the rod enters. Okay, and now according to the barn's perspective, okay, the rod is moving, so the rod is length contracted. So the length of the rod is L over 1 minus v square by c square. Okay, and therefore the rod is shorter than the barn as seen by this observer. And so when the rod reaches this end of the barn, you would say that, okay, now it's shorter than the barn, and therefore what should happen is that now I slam the gate. Okay, and then the question is, what happens to the rod? Does it expand? Okay, and does it become longer? Because now it's come to rest, so it must have the same length as the barn. Okay, so this looks sort of weird. Okay, that the rod, the back end of the rod should expand back to the back of the barn. Okay, and the other thing is, if you look at it from the rod's perspective, this is even weirder, because from the rod's perspective, in the rest frame of the rod has a length L0, but the barn is shorter. Okay, but the barn is shorter. The barn has a length L0 over 1 minus v square by c square. So the question is, how will the person carrying the rod, okay, know when to stop? Okay, because it seems like you hit the back end, okay, and the rod is longer, and so basically you'd have to break through this side, okay, and the person on the other side would not be able to slam the door shut. Okay, so the question is, of course, at rest, we know that both of them have the same length, so it should be possible to come to rest, okay, inside and have exactly the same length for the barn and for the rod. Okay, so the question is, which perspective is correct? Okay, what actually happens, okay, when you run through with the rod, and is it possible to achieve this configuration, okay, where the rod is inside the barn? Okay, and the answer is, if you can draw whirl lines, okay, for the rod, okay, which basically look like Rindler observers, okay, which have the same asymptotes. And you can now imagine that, so I'm in a frame S, which is the barn's rest frame, okay, and in the barn's rest frame at this point, so imagine that these are the two ends of the rod, A and B. This is the trajectory of one end, and this is the trajectory of the other end, okay, and here is the barn, okay, and here's the door, and I'm running in from this side, okay, and I'm running in and I stop over here, okay, and now the rest length is L0, and it exactly matches the barn's length. Okay, and the idea is, the way the paradox is resolved, okay, is that the front end of the rod and the back end of the rod, okay, they do not have the same acceleration as measured in their common rest frame. Okay, they have different accelerations as measured in their common rest frame. And because they have different accelerations in their common rest frame, one end of the rod stops accelerating, okay, when it reaches one end of the barn, okay, and the other end of the rod, as measured in the common rest frame, well, basically this end is slowing down. This end is also slowing down in their common rest frame, but this end is slowing down slowly, and this end is slowing down faster. Okay, and they both come to rest at the same time, which is over here. Okay, and so in fact, what you think of as a rigid rod, right? in special relativity is not rigid in the sense that you can't maintain a common acceleration, okay, or you can't apply the same common force in the rest frame for all points of the rod at the same time, okay. And another way to see this is when you enter the barn, okay, the point where this end reaches one end of the barn and the other end reaches the other end of the barn, these are simultaneous points as measured in the frame S, okay, and yeah, and you can see, okay, that they're simultaneous, even for the rod, okay, they correspond to the same eta coordinate, if you like. Okay, and let me just, sorry, one last point, okay, which is now if I consider accelerating observers, let me consider accelerating a rod. So this is the front end of the rod, and let's say that this rod has some length L. Okay, and now I accelerate a rod, and this end of the rod is accelerated with an acceleration A in its MCRF. So this will be like a Rindler trajectory. Okay, now the point is that if the rod's length L is greater than c square by A, okay, which gives me a natural length scale, then some of the points on the rod will fall outside the Rindler horizon of this leading edge of the rod. Okay, so what it means is that these points on the rod cannot accelerate hard enough to actually keep up with this point. They cannot maintain a fixed distance to this point. So if the length of the rod is greater than c squared by A and you accelerate one end of the rod with an acceleration A, the rod will actually at some point will have to have an acceleration which goes to infinity to keep up with the other end, and therefore the rod will actually have to snap. Okay, so if you have a rod with length greater than c squared by A and you try to accelerate one end of it with an acceleration A, okay, the rod will snap at some point. Okay, the entire rod will not be able to keep up. Okay, the physical forces on the rod will be, I mean, if you think about a rigid rod, let's say, which has forces between atoms, okay, the forces will be either too great, okay, and the rod will definitely snap at some point. The forces won't be able to hold it together. Okay, so these are kind of like three paradoxes, which this Bell spaceship paradox, the pole and barn paradox, and basically a rod of length greater than some length c squared by A will snap. Okay, if you try to accelerate one end of it. Okay, so these are kind of non-intuitive things in special relativity. Okay, which are just necessitated by the fact that by the fact that speeds cannot exceed the speed of light. Okay, any questions about this?
So you discussed pole and barn paradox for the case when the rod is accelerating, but I think even if the rod is moving with a constant velocity, then also the paradox persists, right?
Okay, yeah. So here I was thinking about the back of the barn is closed. Okay, so the back of the barn is closed, and therefore this end of the rod has to come to rest when it enters over here, when it reaches the back. Okay, so basically it came to rest over here. Okay, so the speed is 0. There's another version of the pole and barn paradox where you can think of this door as open. Okay, and then ask what happens.
Sir, I think I didn't understand what you're trying to say. I mean, what I was asking is, so there's a similar paradox I think happens when the rod is moving with a constant velocity, right? Here you consider an accelerating rod. So even if the rod is moving with a constant velocity, then also
Yeah. Okay, so that's sort of a different version, which is, let me think about a rod. Okay, these are two endpoints of a rod. Okay, and let me just imagine them at a constant velocity. Okay, on a space-time diagram. Right?
yes, sir.
Okay, and now basically the point is that the length of this rod, should appear to be length contracted, right?
Yes, sir.
And the length of the bond should appear to be longer. It should be L0. So let's say the bond is over here. Okay. So suppose I'm in the bond's reference frame. Okay. Then what is happening is first the rod is shorter. Okay, and then there's no paradox, right? As in it goes right through. The front end enters the front end of the rod, let's say, enters here. Okay, this is the front end, this is the back end. So the front end enters the bond here. This is the start of the bond. This is the end of the bond. So the front end enters here. The back end is over here. Then the front end is somewhere inside. The back end enters. Okay, and in the reference frame of the bond, the rod is shorter. Okay, and then eventually it will exit as well. Okay, the front end will reach the back. Okay, and then it can exit. Okay, so in this case there is no deceleration, right? So I'm just assuming that this goes through. Okay, and this is a perfectly consistent picture from the view of the frame S. So the question is then what happens in the frame S prime, which is the frame of the rod. Okay, in the frame of the rod has a fixed length L. Okay, and the bond is moving towards it. Okay, and the bond is length contracted. That is, the bond has a length L0 by gamma, and the bond is moving towards it. So let me just draw it. So this is the word line of the rod, and now if I draw this, okay, this is the word line of the one end of the bond, and this is the word line of the other end of the bond. So you first enter at this time in the frame of the rod, one end enters. Then at a later time, one end enters, and then the back end, okay, of the rod also enters, okay, at a later time. But at the time when the back end has entered, the front end of the rod has already passed through the other side of the rod, the front end has already exited from the back, okay, at this point. And the way you reconcile this is that the front and the back passing through, so the front end of the rod passing through the back end of the barn. Okay, that is this space-time event. Front of rod passing through the back end of the barn. Okay, this event occurs earlier in the rest frame of the rod than the back end of the rod passing through the front end of the barn. Okay, but if I look at it in the frame of the barn, okay, then you see that the front end of the rod hitting the back end of the barn, this occurs later than the back end of the rod hitting the front end of the barn. Okay, so it's perfectly consistent. Okay, it's just that these two events have a different time ordering. Okay, because they're spatially separated events. Okay, they have a space-like separation, so they can have a different time ordering. Okay, so this is one version of the pole and barn paradox where you have a constant velocity, and the question is who is right? Okay, is the pole shorter than the barn, or is the barn shorter than the pole? The answer is both are right, and you can understand it in both reference frames how you can run through. Okay, but the question is what happens if you slam the door shut? Okay, or if the back of the barn is closed? Okay, then what will happen, right? Will you punch right through, right? Or will you come to a stop inside? It must be that you should be able to come to a stop inside. The question is how do you visualize that? Okay, so the way to visualize it is by thinking about this constant accelerations. Yeah, these word lines.
So these word lines of constant acceleration, we will consider them when the compression starts, not for the whole process, right?
Word lines of constant acceleration.
So like the
yeah, you can think of it as instead of something like this, you can think of it as I start with a constant velocity and then I latch onto this curve. Okay, this accelerating curve.
Okay.
Right? It doesn't have to be that I maintain a constant acceleration in the MCRF throughout. Sorry, in fact, it would be like this. You have to have a slope less than c. So you can imagine something like this, right? Constant velocity, and then I start accelerating, or decelerating, and then accelerate in the opposite direction. Okay. Okay, so I think we can stop here, and we'll meet next Tuesday. Okay, and I'll upload these lecture notes soon. Okay, see you. Good night.
Thank you.
Thank you.
Thank you,
Thank
sir.
you.
Thank you, sir. Thank you, sir.